Of this conference,
and he's going to tell us about the Feshbach-Schur renormalization group for the Anderson model.
Okay, well, I just wanted to, since I have the honor of being the last speaker, I wanted to make sure that we make a round of applause for the David Bridges and the other organizers for bringing us together here. And
the people who brought all of the people to this conference actually are Martin Hoffmanova, which is still around, yes, and Zan Botti, who's not here, and also, who else is not here? Oh, Manfred is not here at the moment. He went home yesterday.
okay.
And there's a fourth one, and I can't know it.
Okay, well, now we finally cleared that up. So anyway, I just wanted to say I think this has been a very productive, interesting meeting because as we're now starting to appreciate this, RG is kind of it's like a many worlds interpretation of RG. There's many incarnations, and so bringing together people who are doing different aspects is a very useful thing. And so today I'm going to be talking about a slightly different direction of applying RG, but it seems that RG can do just about whatever you want it to do. So, anyway, maybe this will be a useful point of view for somebody else. All right. Well, this is basically the plan. What I'm going to be looking at is the Anderson model, which I'll get to in a bit of what exactly that is. But it's a quantum particle moving in a random potential, and going to develop a renormalization group framework based on Feshbach-Schur maps, which I'll also explain in a second. What this does is it reduces the dimension of the space on which you're working. Quantum mechanics is essentially linear algebra, okay? So you want to know eigenvalues and eigenfunctions, maybe a little bit of harmonic analysis thrown in to get uncertainty principle. But anyway, so this is really a linear algebra problem of finding eigenvalues in a complicated situation where you have a random matrix of a certain type. Anyway, I'll get to the rest of this soon enough. So let's talk about the linear algebra of a Schur complement, or also called the physics literature, we'll call it Feshbach map. Let's just take a symmetric matrix. If it's in block form, A, B, C, D, and you want to think of D as being basically the gapped modes, so at least relative to some energy, E. So there's kind of like, you want to find all the eigenvalues perhaps of the matrix H, but you find them by looking near the energy E. And then if you let E vary around, you'll get all the eigenvalues. But for the moment, we're going to fix the energy E around which we're going to work.
Is he a number?
Yes. So there's some gap of size epsilon, so this inverse is bounded by epsilon inverse. And let's imagine that the off-diagonal parts are small. Gamma is a small number. Then we can define a Schur complement at an energy lambda by this formula here. And then what are the consequences of this definition? Why is this useful? Let's suppose that epsilon is maybe small, and but still the ratio gamma over epsilon is small. And we're going to work in a neighborhood of the energy E. With epsilon over 2. Then for any lambda in that neighborhood, basically the utility is that the eigenvalue problem for F is equivalent to the eigenvalue problem for H. In other words, if I have an eigenvalue, an eigenfunction, an eigenvalue lambda for F, then that's, I can basically extend this eigenfunction throughout the whole space in this fashion, and that produces an function with the same eigenvalue for the Hamiltonian H. So in essence, if you have these gap modes, they're kind of unimportant. You want to get rid of them and just focus on the modes that actually are relevant for solving the eigenvalue problem. And there's some further properties that may be useful. One property is that this, under these conditions, the Schur complement matrix doesn't depend very much on the subscript. So if I'm working near E, I can move the subscript around, at least in some neighborhood about E, and the variation here is going to be small. So unfortunately, it's not the case that you can simply, if you want to work in this neighborhood, you can't just replace H with F sub E, for example, and expect to find all the eigenvalues of H directly there. You have to move around this subscript. It creates a little complication, but it really is not a very serious one because of this sort of Lipschitz condition. The variation is very mild. Then, okay, the conclusion then is the spectrum of H that we're interested in is in close agreement with that of F sub E. Now, if I'm fixing the subscript in the following sense. So then, if I have the eigenvalues of H, then there are corresponding eigenvalues. I should have put superscripts or tildes or something on them, but anyway, the corresponding eigenvalues of F sub E, and they're not exactly the same numbers, but they're pretty close. Especially they get really close the closer you get to E. All right, so one thing it's useful if you're interested in knowing about gaps in the spectrum, which is a problem that I'm very interested in. If you find a gap in the spectrum for Fe, well, that will translate to a gap for H. Okay, so that's a Schur complement. And as I said, I already said this, I guess. So what we think of it, just like in RG, we eliminate the degrees of freedom associated with the block matrix, subblock D. And F sub lambda is a kind of renormalized form of the Hamiltonian. All right, so now let's talk a little bit about iterating this process. The renormalization group is supposed to be a sequence of steps. That was just one step. And actually, I'm going to take a little bit of an excursion here, away not into the domain of Anderson models and things, but to talk about block spins for a moment. Basically, this is like an addendum to Martin Lohmann's introduction to these block spin ideas, to show that actually there's kind of a Feshbach-Schur underpinning that as well. So, all right, so let me just, for a moment, just the next slide or two, talk about the kinematics of block spin transformations. This takes sort of the canonical model of phi-4, and you have this H, which would be like the Laplacian, and some potential. And what typically you want to do is you want to project onto some energies, maybe less than 2 to the minus k in step k of a renormalization group. But if you just go to the momentum basis for the Hamiltonian, then you have plane waves, and that's inconvenient because it kind of messes around with the locality of the problem. So instead, if you want to work more in position space, you introduce block fields. So I'll use psi for a block field, which is really the average of the original field on a block B of x centered at x. And then what you can do is you can basically, you want to define a block diagonal decomposition, if you will, by choosing an appropriate basis. So the field is written as the block field times a constant function plus this fluctuation field chi. And of course, in each block, this really has just one dimension, and this has dimension L to the d minus 1 if it's an L by L block. And we could choose a basis for these modes, and that means there'll be L to the d minus 1 basis vectors on each block. All right, so this defines then a block decomposition of the Hamiltonian. We can, now D, basically, if we, the inverse of that, I should have put inverse. Inverse is the fluctuation covariance, and you find that because it's the high momentum modes, that the inverse exists. It's bounded by some 1 over epsilon, just as in my basic lemma that I wrote at the beginning. These terms B and C, they're going to couple the block phi and chi. All right, so this H is, of course, no longer. If I had done momentum eigenbasis, then there wouldn't have been any B and C. But since I've chosen this other basis to work in, there is a B and a C. So what we need to do is, and as explained by Martin a couple of days ago, we need to shift this fluctuation field to center the Gaussian integral. And the shift, in fact, is given by D inverse C, because if you plug in this shift into the quadratic form that we're working with, we have this linear piece that we want to get rid of. And the shift exactly cancels that linear piece, but it produces this extra bit, an extra quadratic term as a function of psi. And so you can rewrite this as a new quadratic form with no cross terms, psi f0 psi and chi d chi. And f0 then is the original one plus this correction, a minus b d inverse c. So in fact, this is exactly the Schur complement that I wrote down before. We can, of course, think of this translation function. We think of this as the minimizer of the quadratic form given the values of psi. And it sort of plays a similar role as this combination of operators does here when in the Schur complement. Over here, we see a D inverse C phi, which is a way of extending the eigenvector from the small space out into the rest of the space. Okay, so anyway, so that's the end of a little bit of a digression. Show connection. In fact, when I was first, this is sort of my background from years ago, was working in this kind of picture, and then I started playing around with Schur complements, and it all seemed somehow amazingly familiar, so especially the multi-scale aspects of it. All right, so now let's go and apply this analysis to random Schrodinger problem. So here's the Hamiltonian. Let's take a simple Anderson model where gamma, again, is a small number times the Laplacian, and we have a random potential V. The V's are ID random variables, and I'm particularly interested in the case where it's the discrete distribution. So I'd like to take this distribution, which is uniform on a set of n values between 0 and 1. And of course, it might be nice to consider the case n equals 2. This is sometimes called the Anderson-Bernoulli model, because then you have a Bernoulli distribution for the potential. And this is a very nice model, sort of a canonical example in the random Schrodinger class, because well, you consider, in fact, you can get rid of this gamma and just consider minus Laplacian plus V, where V is 0, 1, and that's really very similar to, it's kind of like the Ising model of random Schrodinger, because it's nearest neighbors and just zeros and ones. It's very simple to define. What we'd like to do is to show exponential decay of the eigenfunctions of this operator, which is known as the localization problem. And furthermore, I want to get into the details of the spectrum in terms of how likely is it for you to have a degeneracy or a near degeneracy in the spectrum. Of course, we're nowadays with random matrix theory, we're very interested in eigenvalue statistics and different questions there. This issues of controlling degeneracies turned out to be extremely relevant for results that I was trying to obtain in the many-body interacting problem involving random potentials. And so this is a way of experimenting with these ideas of how does the environment exactly break degeneracies in simpler situations, non-interacting systems. Okay, yeah, so Anderson-Bernoulli has been considered before, but Bourgain-Koenig, famous result 2005, but that was replacing the lattice ZD with RD. And actually there's a couple more recent results that I'll mention a little bit later on, but the lattice problem has been open for quite some time. Of course, the methods on random Schrodinger in general, let's say if you take a continuous distribution for V, has been the subject of a lot of study over the past, I don't know, 30 or 40 years, going back to Froelich and Spencer in '83 when they were first. In fact, many of these tools that I'm going to be mentioning today are actually go back to that paper. So the result that I can prove about this discrete disorder problem, well, here it is. So just for notation, let I delta of E denote an interval about E of radius delta. N(i) is the number of eigenvalues in that interval, and so this is a density of state bound. It says what's the expected number of eigenvalues in a small interval about E. Ideally, you would want this to go to 0 with delta. Would give you a kind of some sort of continuity of the distribution of energy levels. And the quantifiers are important here. If I fix P can be anything I want, then we take N large and then gamma small. So anyway, we can think of P as being large, bigger than D or 2D or something. This does go to 0, but not very fast. That's kind of a problem. Normally, if we did continuous distributions, this would go to 0, be proportional to delta. Now we have a power of log delta, so it doesn't go to 0 very fast, but it does go to 0. Can also look at these probabilities of degeneracies. Now, degeneracies are a very big feature of the problem of discrete disorders, because if you think about it, if you take one site and you say, what's the probability that I have an eigenvalue in an interval with delta? Well, the probability is 1 over n, independent of delta, if it's just one site. That's the mass of that probability atom. But somehow when you go to a much larger system, there's effect of nearby sites have a way of spreading things out and smoothing out this discrete distribution. And this discrete distribution becomes has many more atoms, and in the limit of large lambda, it becomes a continuous distribution. So that's an interesting process to see this flow from discrete to continuous. But it's a tricky to do this on the lattice. And then we have also decay of the eigenfunctions, both pointwise and in mean.
John, what is this dimension independent?
Yes. All right, so let me talk about, that's kind of where we're headed, but I'm really more focused on the techniques here that people might be interested in. So let's talk about how we go about getting such a result. Well, the thing is, we want to define this block decomposition, right? We're going to use Schur complements, so we have to have a notion of the resonant modes and the non-resonant modes. So once again, we fix E, and we're going to then define the resonant set R1. This is a subset of the lattice. It's all the sites I such that Vi minus E is smaller than epsilon. All right, so here epsilon is 1 over n, basically. So if you think about it, essentially what we're saying is that the potential has to have, let's say E is, I don't know, 1/2. If that's one of the values of the potential, then the VI there has to be equal to that one value that it's allowed to have, because any of the other values that are allowed, they're spaced by essentially 1 over n. And so if it's not equal to the one value that fits in this neighborhood, it's going to be non-resonant. Very simple. So the probability of a given site being resonant is actually 1 over n. Maybe I should have put 1 over 2n or something like here, but you get the idea. So then we have a block decomposition of the Hamiltonian based upon the resonant sites, which defines the block A, and the non-resonant sites, which define the block D. They're restricted to is the restriction of the Hamiltonian to those two subsets of the lattice. Of course, then there's interactions, couplings between the resonant set and the non-resonant set. Those go into the matrices B and C. But we have we put a small factor, gamma, in front of the Laplacian, so the off-diagonal pieces are small. And so it's clear then we're in the situation then where B and C are small matrices. And we're in the situation that I wrote down in that first lemma on the Schur complements. We can invert to form the resolvent, d minus lambda inverse. It's going to be bounded not only for E, but also for all lambda in some neighborhood of E with epsilon over 2. So as a consequence, we've essentially reduced the problem to a problem purely on the resonant sets. If psi is an eigenvector of H with eigenvalue lambda, then psi, which is this extension of phi, then psi is of this form where phi is an eigenvalue of the Schur complement matrix. And the decay of the resolvent implies that essentially all these eigenfunctions are going to have peaks on the resonant set. They're going to decay exponentially away. All right, so that was sort of like the first step. But we want to do an iteration. The first part of the iteration would involve defining connected components of the resonant set. We want to do kind of a locality thing. So we may think of these places. So this is going to be R1. These spots in the lattice, which are relatively rare, right? Because remember, n is large. The probability that any given site is in the resonant set is 1 over n. But at the moment, the resonant set is all these things together, but it makes sense if they're clumped together to call this a component. This is a component, this is a component, that's a component. There's going to be some proximity rules based upon a length scale, but for the moment, just think of it in terms of nearest neighbor or next nearest neighbor, something like that. Some rules for defining what it means to be connected. Now, having defined these components, what I want to do is something like what you do in quasi-degenerate perturbation theory, where you have a bunch of modes which are nearly degenerate, and you want to do some kind of perturbation theory. Well, what the giants of the past told us is that you need to diagonalize the submatrix corresponding to those modes, and then consider the perturbation. And that's exactly what we're going to do. For each of these components, we're going to define some kind of a neighborhood. And we define the connectedness in such a way that these neighborhoods are not going to overlap. So each one of these components is going to have a neighborhood, what I'll call B bar. If B block, from quasi-degenerate perturbation theory, that's the language from that. B bar is going to be this neighborhood. We introduce a sequence of length scales, in fact, and this is going to be just the first element of that sequence. So then we're going to change the Schur complement. Instead of considering the Schur complement on the whole lattice, we're going to consider it just in the neighborhood B bar. And I'm going to call that F tilde, which really depends upon the block B. So now D, and I'm not going to introduce another notation for that, but D is the matrix is restricted to B bar minus B instead of lambda minus B. One way to, of course, the resolvent we know decays, but one way to see that is to think graphically in terms of random walk expansions. So the resolvent, if you expand the resolvent with respect to the diagonal, as many of you probably know, you get a sequence of a sum of random walks, just a Neumann expansion. Graphically, we can interpret this as a line that moves around. But when we consider the F tilde, these are the lines which remain within the neighborhood in question. All those graphs which contribute to the original F would include graphs, for example, like this, which go from one block to another. Or they might go farther away than the edge of B bar and then back. These additional graphs are just thrown away when we consider F tilde. Now, if you think about it, the graphs that we're throwing away all are going to be longer than twice the radius of this B bar neighborhood. So if that's a moderately large number, even in the first step, we can take that to be a moderately large number. We're going to have many powers of gamma. Gamma to the, let's call it gamma to the L, where L is the length of the graph, the length of the walk. And of course, L is going to be bigger than 2L1 for graphs neglected. So that means we have a very good approximation for the eigenvalue problem. That's what you're supposed to do in quasi-degenerate perturbation theory. And in fact, we can make this a little more quantitatively. The original Schur complement matrix is approximately a direct sum of these F tildes, and the error, as I stated over here, is gamma to some large power. Now, really, this is analogous to the statement that you might make at the very beginning to say, well, we have a strongly diagonal dominant situation. H is really essentially a diagonal matrix with corrections of order gamma corresponding to the off-diagonal pieces of the Laplacian. So we're just doing this in a kind of a block sense. And note that by Weyl's inequality, the spectrum doesn't move any more than the norm of the perturbation. So all the eigenvalues of H are going to be within gamma of these potential values, and similarly the eigenvalues of F are going to be within gamma to this power of the corresponding eigenvalues of these F tildes around each block. So we're getting a sense then that these approximations, as we do this better and better, we're going to get better and better idea of exactly where these eigenvalues are. All right, so now with those preliminaries out of the way, I can just talk in general terms about how the iteration proceeds. So as I said already, we have length scales. We can take them to be 2 to the k length scales. Then there's going to be an energy window, which I can denote by epsilon k, the width of the energy window. It's going to be gamma to the lk, and this corresponds really to this gamma to the L associated with the graphs that exceed this LK neighborhoods that we're going to introduce in the kth step. Now we're going to have a kth step resonance set, and those are going to consist of the blocks that are still resonant to E within this now much smaller distance epsilon k. Then we have to, of course, do proximity conditions as well. That's going to be a multi-scale version. These k-step blocks are going to be separated by a somewhat larger distance, lk to the 3/2. And then it's going to have a neighborhood, as I mentioned, with lk. And there's some details in this which actually go back to way back to Froelich Spencer, 83. It's all very similar to that. So then we do this iterative Schur complement. We get the kth one from the k first. We do a block decomposition of the k minus first Schur complement like this. So this A matrix is the block based upon those still resonant blocks. And the D ones consist of the ones that we just lose in that step. And then we define the usual formula for the kth Schur complement. And one way to envision this is that we have sort of really bad blocks here that are still around in the kth step, right? And then we have walks that go, and then we have sort of moderately bad things here. But these are the ones that are removed in the kth step, or remove when we go to rk minus 1 to rk. So we kind of essentially treat this as just a generalized random walk, and we plow right through these ones which previously were considered too singular to work with. But since they're not resonant on this tiny scale, we can use the length and the very long decay length to compensate for the small denominator associated with the near resonance of these sets. So these go away. We're left with these remaining set RK, and we keep on going. And anyway, that's the procedure. Now the obtaining estimates. Okay, so it's important to demonstrate that the resonant blocks, which can be thought of as percolation clusters, they can't percolate. Essentially, in some very crude sense, if you have a resonant block, for all you know, this could be a random matrix in here, and basically every site could be connected to every other site. You're not going to have any decay of the eigenfunctions associated with that block internal to the block. So then if the block somehow takes over the whole universe, you won't have localization anymore. And the whole procedure would break down. So it really comes down to the fact that localization can be thought of as a situation where there's no percolation of resonances. Now we're making connections on longer and longer distance scales, but the blocks are also being dropped. So there's sort of two competing effects. They get bigger, but we drop some of them, and we have to make sure that one effect dominates the other. Essentially, we want to know that the expected size of a percolation cluster stays bounded, and this will be true uniformly in K as long as the probability of a block remaining resonant is bounded by Lk to the minus p for some p bigger than d. So anyway, so just it's essentially an integrability question. Probabilities have to decay faster than integrably to be guaranteed that there's no percolation of resonances. So probability estimates, this is kind of the borderline for this workability of this method, but we're able to achieve that. Now, and as I mentioned, the continuous distribution, it's much easier because you see probability actually goes like the length of the interval by the Wegener estimate. And so this is going to be exponential in Lk rather than a power in Lk. So very different situation as far as probabilities are concerned. Now for a discrete distribution, I mentioned this already, the narrowing of the spectral window doesn't necessarily guarantee that the probability of resonance goes down. So that's really where the hard work goes into with this problem. So what we need to do is demonstrate eigenvalue movement and separation, if you want to talk about spectral statistics, based on the effective potentials in the annuli B bar K minus b bar k minus 1. So these are the potentials which are brought in when we go from fk minus 1 to fk. Here's our resonance center. We have b bar k minus 1, and then we have an annulus as we go to the larger neighborhood b bar k. And the effect of these potentials are going to be small because they're going to involve diagrams which go through the first neighborhood. But they will hopefully wiggle the eigenvalues around a little bit to make this, get these probabilities to go down with k. So now we're going to get into a little bit of a digression to the question of when can we be assured the eigenfunctions themselves do not vanish? The effect of this potential on the eigenvalue is essentially going to be proportional to the square of the eigenfunction at this point, just by first order variation. So you need the eigenfunction to be non-zero in order to get a non-zero effect. And some lattices, like the Kagame lattice, you have these compactly supported eigenfunctions, and there's no guarantee that there will be an eigenfunction that's non-zero anywhere. But the rectangular lattice is better in this regard because you can't have eigenfunctions decaying faster than exponentially in all directions. So if let's say you go to the boundary of some box, and somewhere along that boundary of the box, it has to be at least no smaller than exponentially in the radius of the box. This then basically implies that there are going to be influential sites where an eigenfunction has a lower bound, pretty tiny lower bound, but it is a good lower bound, essentially gamma to Lk. That's the distance out to whatever annulus you're talking about. So anyway, the idea is we only really going to use one site in each annulus, take the most influential one, and it's going to split the isolated splits an isolated eigenvalue into n values as you vary that potential, and the spacing will be essentially the same order. And then if you take a slightly smaller energy window, the probability that it remains in that window under the perturbation is going to be proportional to n to the minus k. I mean, we pick up a factor of 1 over n with each step of the RG. So if we've done the k steps, it's going to be probability n to the minus k of remaining in the window. N being, remember there was epsilon was essentially 1 over n, right? So, and then, let's see. So, sorry. This is Lk is essentially 2 to the k. So if you just take logarithms of this equation, you see that p is essentially the logarithm of n. N being large, we can get p bigger than d. So that's what we need for the resonance not to percolate. Now, the more complicated situation of like I drew here, you have a bunch of, this is not just one site, but a whole bunch of sites here. They're all resonant. So you may have a degeneracy here. Maybe there's an n-fold degeneracy. When you add this perturbation, it's actually going to be a rank 1 perturbation on this a matrix, which is essentially proportional to the identity matrix to a high degree of accuracy. And what that's going to do is it's going to push one of those eigenvalues out of the interval that you're working. So it basically breaks down the degeneracy from n to n minus 1. And if you do this n times, then eventually it's going to break down to the previous case with an isolated eigenvalue, and then it can be blown off at that stage. Anyway, so this is it's a delicate analysis here to work out in detail. Is constant worrying about breaking of degeneracies. In particular, you need to make sure that the corrections to this leading term are all smaller than the leading term, which means that's kind of the reason why we have to take these geometric length scales. We have to make sure we go far enough out, sufficiently small so that gamma to the LK is upper bounds, which maybe go as gamma to some fraction of LK. When I go to 2LK, it's going to fit inside the lower bound that I obtained in the previous step. So in the end result then is essentially kind of a Cantor splitting. With each step, this occurs again at a logarithmic scale. Eigenvalues then get split as I vary one potential. They split again as I vary another potential, and so on. And gradually, it looks more and more like a continuous distribution. And this, because of this logarithmic length scale, that gives us this logarithm with respect to delta. There's another little digression here, which is, has to do with the difference between the lattice and the continuous case, which was considered over 10 years ago by Bourgain and Koenig. They faced very, very much the same issues. They wanted to know that these eigenfunctions were non-vanishing in some places. And actually one of the main results of this celebrated paper is the fact that they had a quantitative form of unique continuation, which says that if you have an eigenfunction of Laplacian plus v, now in the continuum, and you average it over some disk or ball of radius 1, let's say, it's not going to decay arbitrarily fast. It can't decay any quicker than essentially y to the 4/3. And in fact, it's possible to realize this faster than exponential growth for complex potentials. And it's been conjectured that this does not happen for real potentials, but at this point we have to, or they certainly had to allow for that possibility, so they got this very weak lower bound on the size of the eigenfunction. On the plus side, they could get it anywhere they wanted. Whereas on the lattice, I only can really use it once per annulus. So if you want to know what the analogous problem is in ZD, and this has actually been a subject of some work in recent, in the last couple of years, there are certainly examples. For example, here's an example on 2 dimensions of a solution to minus Laplacian minus 4 psi equals 0. And it's clearly, it vanishes on a very large set. Of course, if we extend this off to infinity, it's not a normalizable eigenfunction, but at least it shows that things are very different here on the lattice as compared to the continuum. What you do know is that if you have a place where the eigenfunction is non-zero, that there's a kind of a light cone going down in ZD, and you have a lower bound like this for at least one x in the boundary, one little x in the boundary of this box x, somewhere on this 45-degree light cone of this region R, which can be thought of as a block or a localization center. And so actually there has been some results recently, specifically to 2 dimensions. The Landis conjecture actually, I guess, is solved in dimension 2 by in 2015. There is some kind of form of Euclidean continuation that by these fellows proved about a year ago in ZD, and this was used, I just learned about this last night on this paper, to prove localization near the edge of the spectrum for the Anderson-Bernoulli model. So this is a subject of active study, exactly what the situation is in the lattice, and is there any echo of the unit continuation on the lattice. As far as I have been working on the Anderson-Bernoulli model with Svetlana Mayboroda. We started working on this last year at Princeton, and so of course I have this setup which is very nice for large n, and we're trying to understand what needs to be done to adapt that to the n equals 1. Well, of course, one of the problems is that, really the key problem is the fact that, remember I said p is log base 2 of n, so that's not very large if n is 2. And so a fundamental shift is necessary. You can't, these geometric length scales are actually not going to be sufficient, I think, at least in the procedure that that I have is not going to work. So we have to come up with a way of exploiting more of the randomness in the environment in order to get better decay of probabilities with distance. So I guess I mentioned this earlier, this Cantor condition, which is basically the upper bound of one generation has to fit inside the lower bound on the previous generation. That's what led to these geometric length scales, but we have to do better for n equals 2. Basically, we want to do a number of shells which grows linearly with distance rather than exponentially with distance. Another feature here with the, I guess I didn't mention this part of this slide, but when you have n equals 2, you have many, many degeneracies. You have to compensate. It's not necessarily going to get localization for all energies, but we take E small, Lifshitz tail regime. And then to get spectrum near E, we have to have wave functions that vary rather slowly. And that means that to get energy small, we have to have essentially a whole bunch of zeros all packed together in a small region. And this is essentially a Lifshitz tail large deviation argument to say that the distance or separation between these very rare places where you've got a vast supermajority of zeros is going to grow like the energy, exponential of the energy of the d over 2. So this kind of gives us our small parameter then. We don't need a gamma in front of the Laplacian anymore. We have this, or with 1 over this, is a small parameter which we obtain by taking E small. Okay, so anyway, so as a consequence of having E being small, that means the decay length is going to be many lattice steps, and it's a little difficult to pin down the location where the eigenfunction is guaranteed to be big. And this is another issue that is very aggravating, but anyway, we have some ideas, hopefully that will work out to deal with that. So anyway, that's work to be in progress, and I thank you for your attention.
Thanks very much. Are there some comments or questions? Now, this unique continuation is a very active, this Landis problem is a very active subject at the Institute at Princeton.
Yeah, right. Yeah, it was very informative. Of course, several of those authors, Logunov and on this lattice thing, they were across the hall from me, and so I talked with them quite a bit about these problems. Yes?
Some time ago, I got interested in the question what would happen if you have Zeeman interactions of a spin with random directions.
Yes, okay.
Unit length, and this was sort of a fairly difficult problem. Bourgeois made some contributions about the density of states. Is that something you could do with your methods?
Yeah, I think
also have this huge degeneracy of eigenvalues for the unperturbed operator before you introduce the hopping. And so it's a little like here that you have to see.
So, I didn't know there's a degeneracy from kind of like the hydrogen atom degeneracy where you just have...
Oh, you see, on site you have a sigma dot n. Sigma is the vector of Pauli matrices.
Yeah.
The eigenvalues are plus or minus 1 if n is a unit vector.
Yeah.
That's on every side.
Oh, okay, yeah.
Or you couple, you have this enormous degeneracy, but then once you couple, you start to feel that the directions are different, and that spreads out the spectrum.
Yeah, right, yeah. So that's exactly the type of problem that this method is designed to do, because, and really that's, unless you think of the unique continuation of Bourgain-Koenig as, in some sense it's the same thing, but there's hardly any methods out there to deal with how you get, take account of the disorder in the environment to smooth out the density of states. And this is explicitly designed to do that. It does require, though, you have to be able to pinpoint some place where you know that an eigenfunction is non-zero. So that's always a weak point that would have to be checked as far as your model is concerned.
Any other questions? Okay, let's thank John and all the organizers again, please.